so what quantum numbers do is they tell us the address of an individual electron. Okay, so just like our addresses are 4 parts, right? House number, street, city, zip code, right? It tells us all these 4 parts. The address of electron is 4 parts also. You'll remember, maybe, if we remember quantum numbers are written, not like that. They are written like this, like 1, 0, 0, 1/2. Okay? This gives us the address of a particular electron. Okay, so it's written with 4 parts, and these 4 parts are given usually in parentheses in just like a list format. Okay, so let's talk a little bit about what each of these 4 parts means. The first part of the quantum number is represented with an N. You don't really need to know the letter that's associated with it as much as what it represents. Okay, so this tells us the energy level, the size and the energy level of the orbital. Maybe insert level there. Energy level of the orbital. I don't know if I left that off on purpose or an accident, but the size and the energy level of the orbital. And so that would mean, like, if I have an electron in the 2s orbital, my quantum number would start with 2. Right? The first part of my quantum number would start with 2 because it's telling me the energy level or like the shell level that electron is located in. Okay? Typically when we ask for the quantum numbers of, let's say I would ask for, give me the quantum number for the last electron in aluminum. Right? So if I'm looking at aluminum and I want to see the last electron that goes in, that's electron number what? What would be the electron that goes in last for aluminum? Electron number 13, right? 13 electrons in aluminum, 13 is the last one to go in. And based on what we know about aluminum, what shell would it be going into? What kind of orbital would it be going into? A 1s, a 2p, what would it be going into? It would be going into a 3p orbital based on what we know about aluminum. And so we're going to be able to go even further into that. The quantum number is going to be able to tell us the level, the shape, the version of the orbital or the orientation of that orbital around the nucleus, and it's going to tell us, is it the first electron that went in or the second one that went in? So it's going to tell us the spin state of it as well. So first part tells us the energy level, and that comes right from just like the version of the orbital. So 3p, 4d, it would be a 4, right? All of those different ones right there. The second one is called the angular momentum quantum number, which sounds a lot fancier than it really is. All this tells us is the shape of the orbital. Okay, and I'm going to give you the values that correspond with that on the next slide. Okay, the shape of the orbital has a numerical value assigned to it. So if it is an s orbital, that means the quantum number for that orbital is 0. Okay, so you'll need to make sure you know this table highlight or whatever. If it's a p orbital, the second part of the quantum number would be a 1. A d orbital would mean it's a 2. An f orbital would mean it's a 3. So I usually just say it literally on my hand. S, then p, d, f. S, p, d, f, right? It helps me just know what it's supposed to be, right? All right. The third part of the quantum number tells us the version of the orbital that it's in. So let's look at a p orbital, for example. When I draw the orbital diagram for a 2p orbital, I draw it in 3 lines, right? Because there's 3 versions of the p orbitals. This is going to tell me, is my electron in this orbital, this one, or this one? Okay, and I'll kind of walk through that here in just a second. But it's gonna pinpoint to me which version of my p orbital is it in. And like we saw yesterday, there's a px, a py, and a pz orbital. It's going to be able to tell me which version of the orbital is it found in. Okay, that's what the third part looks like. And then the last part tells me, is it the first electron that went in or is it the second? Okay, is it the first one that went in or the second? And is it spinning in the positive direction or is it spinning in the negative direction? So that's what the fourth part tells us here, the spin number. So if I was locating this electron right here, right, that would be the second electron that went in that orbital, and it would have a negative spin state. Okay, so let's kind of put these things together. The only 2 options for the last quantum number is positive 1/2 or negative 1/2. Those are the only 2 possible options for the fourth part of the quantum number, positive 1/2 or negative 1/2. And if my electron is pointing upward in my diagram, then that means it's a positive 1/2. If my electron is pointing downward in my orbital diagram or my orbital notation, that means it's the second electron that went in, which is the negative 1/2 spinning direction. Okay? The third quantum number has lots of options, but we're going to go through how we determine what that is. The second quantum number only has the options number 0, 1, 2, and 3, because those are the only shapes that we talked about, right? S, P, D, or F. So those are the only possible options for the second part of the quantum number. The first part of the quantum number, could it ever be a 0? Could the principal quantum number ever be a 0? No, because we don't have 0 level shells, right? It could be really 1 through 7. Okay. This third one is where it just gets a little bit trickier to identify, and we'll see how we do that here in just a sec. Okay. What questions do we have so far? Is this coming back to us a little bit, quantum numbers? Okay, yeah, Leaf, go ahead.
If it's a noble gas, could it be 8
on this part?
Yeah.
Right, no, because a noble gas, the reason it only goes to 7 is because there's only 7 levels to the periodic table, right? So francium would be like 7s, and so all the way over there would be like 7p. There's no 8 level energy. We'll do the quantum number of a noble gas here, and I'll show you what it would look like. Okay. Let's go ahead and try one. We'll just start out with a noble gas. That's fine. Let's do the quantum number for, let's do argon. Okay, let's find the quantum number for the last electron in argon. And so the reason it's written like that, the last electron in argon, is because theoretically I could find the quantum number for any electron in argon. If I wanted to find the electron for the first, if I wanted to find the quantum number for the first electron in argon, it would be like finding hydrogen's quantum number, right? That's essentially what it would look like. If I wanted the second electron, it would look like I was finding helium's quantum number, right? I can find any electron, but usually I'm going to find the last one. So argon is in 1, 2, 3p6, right? 3p6. So when I want to identify the quantum number, I draw out the last part of the orbital diagram for that electron. So 3p is my orbitals. And then do you remember how we fill in our electrons? 1 across all the way, 1, 2, 3, 4, 5, 6. And so I'm trying to identify this electron's address. Agreed? I want the 6th one, the last one to go in. So I'm going to start with a quantum number with the principal energy level, which is 3, right? Because it's a 3p. Comes right there. Then what's the second part tell us? The shape. So S is 0, P is 1. Okay, so now I need to know which version of the orbital is it in. So this is how this part works. The values for the third quantum number can range from negative this number to positive this number. Okay? -1 to +1 in this case. The way we know that is because I label my orbitals in that way. -1, 0, +1. Right? They range from negative m to positive m. So in this case, they range from -1 to +1. I just label those orbitals. And so I look, well, my electron's on the version that's +1. So in this case, it would be in a pz orbital, right? If we were going to label it all the way down to that, but we don't have to. All right, last thing I look at is going to be what direction is it spinning? Okay, is this one going to be +1/2 or -1/2? -1/2. And there's my quantum number. There's the address that goes with that. Okay? This would be the quantum number for the last electron in argon. Now, couldn't this also be the quantum number for the second to last electron in potassium? All right, you see where potassium is? Potassium's 1 more than argon. So if I wanted to know the second to last electron in potassium, wouldn't it be this exact same quantum number? Yeah, because if I wanted to go to potassium, I would go 4s1. The second to last electron that went in was that one. Right? So you can just kind of look and see if I wanted the third to last electron from calcium, it would still look the same as argon. You know what I'm saying? Okay. Let's try another one here. Give me the quantum number for the last electron placed in nickel plus 2. So nickel, but we've got the ion version of nickel. So how does that change things? Two more or two less electrons? Two less, right? Two less. We've got a positive charge, which means I've got less electrons than I should have. So think about this. That if it's nickel plus 2, that means it looks like what? Looks kind of like iron. Okay, so we can kind of build our orbital diagram based off of really what iron would look like. Or you could do nickels and take 2 electrons away if you wanted to too. That would be fine. But we see nickels in the 3D orbitals. So I'm going to draw all the way out. 1, 2, 3, 4, 5. These are 3D. And then, go ahead, sorry.
So, I'm going to do it as iron.
Yeah, you're going to it's going to be the same as the quantum number for the last electron in iron. So you could solve it that way if you wanted to. Okay, if I was going to do nickel, let's just think about nickel by itself right now. It's 3D8. I would go 1, 2, 3, 4, 5, 6, 7, 8. Right? But I've got 2 less electrons than I need. So I'm going to take away those last 2. And that leaves me with nickel plus 2, which means I'm looking at this one, which is 3D6, which is essentially iron. Right? So that means I'm looking for this guy right here. Let's go ahead and start building our quantum number. My first part of my quantum number comes right here from the 3. The shape of my orbital comes next. So what number goes with a d orbital? 0, 1, 2. Yeah, okay. SPD, yep. 2. And then I need to figure out what version. So I label my orbitals from -2 to +2. -2, -1, 0, 1, 2. And so what version of my orbital is? Yeah, -2. And then is it the positive one or the negative one? -1/2. So the -1/2 tells me it's the second electron that found its home in that orbital and it's spinning in the negative direction.
So if you have an S orbital, the third number will always be 0.
Perfect. Yes. If my shape is ever S, it's going to go 0, 0 in the middle of my quantum number. Yes, good question. Okay. The reason that would be is let's say if I have 2s orbital, if my S shape is 0, it's only going to range from 0 to 0, right? Yeah, that's good. All right. What questions do we have about forming the quantum number?
I don't have a question about that. But,
Okay. A quantum number, you're going to identify the element that it's coming from. Okay. So let's say, we're going to identify the element. And when I give you quantum numbers, I'll usually say, this is the quantum number from the last electron in some element. You know what I'm saying? I would not give you the quantum number and then expect you to guess the ion it's coming from. You know what I'm saying? If I give you the quantum number, it's got to be from a ground state atom. Okay? So 3 tells me it's a 3, and then this number 1 tells me it's a 3p orbital. So I'm going to go ahead and draw that out. 3p, right? This 0 tells me it's going to fall on what orbital?
Y.
Okay, yes, the y one or the middle one, yes. So I'm going to draw them out, -1, 0. That means I'm looking at, my attention is focused on the middle orbital, right? Is it going to be the first electron that goes in or the second? The first. So I'm going to fill in my electrons, and I'm going to stop right there because I want the positively spinning one, or the first one that goes in. So that means my attention is on that electron right there. That's what the quantum number is for right there. But now I have to go back and think, okay, what element is 3p2? And it is silicon, I think, right?
Mm-hmm.